This is a continuation video of one that you have previously watched. The essential question for that video was, what shortcuts can I use to prove that two triangles are similar? And in that video we talked about how if we can find that two angles from one triangle are congruent to two angles of another, then the two triangles must be similar. And we went through some questions to show how we can use that to prove similarity. Now, as a continuation, we're going to look at two more shortcuts for proving that two triangles are similar. The first one is side-side-side similarity. Now, you've learned last year that side-side-side can actually also prove congruence. If all three sides of one triangle are congruent to all three sides of another, then we can prove those two triangles are congruent. In today's lesson, we're learning that side-side-side also can prove similarity, but look at the definitions a little bit different. So we look at this and say, if the three sides of one triangle are proportional to the three sides of another triangle, then the triangles must be similar. So now we're looking at proportionality, not at congruence. Let's see how this works out. Now I'm going to teach you guys a method of doing this that works every time. It'll keep you from being confused on which sides you're supposed to be matching up. So if you're given two triangles and you're given the measures of all three sides and you're being asked the question, are these two triangles similar? Here's the strategy that you will use. It's difficult to see whether these triangles have been rotated, reflected, or possibly rotated and reflected. So we don't have to worry about that. Here's our strategy. You're going to put a circle around the biggest side. Around the biggest side. So, take a look at these two triangles. The biggest side of the first one is 15. I'm going to circle it. And the biggest side of this triangle is 5. The next thing you're going to do is you're going to put a square around the smallest. Around the smallest side. So taking a look at our first triangle, 9 is the smallest side. And then on our second triangle, 3 is the smallest side. Now notice, I didn't have to figure out whether they were rotated, reflected, however they were changed. I just need to put a circle around the biggest two sides, the biggest one of each triangle, I guess, and then a square around the smallest side of each triangle. And that's all you have to do. Just like matching up vertices, which you've done before, we're not going to put any mark on the middle side. That one we just know goes together because it doesn't have a mark. Now here's how you can figure out whether these two triangles are similar or not. If the proportion of 15, or the ratio of 15 and 5, is equal to the ratio of 9 and 3, and that's equal to the ratio of 12 and 4, then we know these two triangles are similar because we're actually proving the sides are proportional. Or another way to say it is the sides have grown or shrunk by the same scale factor. So let's take a look at these three things. We're going to take the biggest side first, and let's check it out. We got 15 on the top triangle, and we've got 5 on the bottom triangle. That reduces to 3 over 1. There's our scale factor from going from the smallest to the biggest. Now, here's the only thing you guys need to be careful of is, if for the first ratio you picked the number from this triangle right here, then every other scale factor you have to pick first from this triangle. You can't switch back and forth, kind of like the rules on your proportionality statement. So now that I've actually taken 15 from this bigger triangle, when I compare the smallest side, I got to take the side from that same first triangle. So the top of your ratio has to always be from the same shape. So we're going to compare 9 to 3. Divide top and bottom by 3, and you get 3 to 1. Hey, so far we have a scale factor of 3 to 1. Now let's go ahead and compare the final side. Again, let's go back to our first triangle, the one we've always put on top. We're going to put the 12 on top, and we're going to compare that to 4. We divide top and bottom by 4, and that reduces to 3 over 1. And now you see that all three of these scale factors are the same. So I'm going to put on there same scale factor. If we have the same scale factor, then we have proportionality. And if we have proportionality, then we can see all three sides are proportional, so these triangles must be similar. So then we can say then they are similar. Oops, I put the word are in there. Then they are similar by the SSS theorem. So there's a way we can actually prove that two triangles are similar. It's a shortcut. We don't have to look at the angles. We can just look at the three sides. So let's take a look at how this plays out in a question. Here's a typical question you might see on a test or a quiz. Is triangle MNP similar to triangle QRS? Now, we've learned, class, that you can match up your sides by writing a proportionality statement. So if you want to do that, you can go ahead and do that. You can write MN over QR is equal to NP over RS, which is equal to MP over QS. That will also tell you which sides match up to which side. But I can tell you the shortcut is, if you know the side lengths of all the triangles, you can just follow this same principle that we did before. We're going to circle the biggest side. The biggest side of the top triangle is 7.5. The biggest side of the bottom triangle is 5. Now we're going to put a square around the smallest side. The smallest side of this one is 4.5. Smallest side of this one is 3. Now you can see these triangles actually haven't been rotated or reflected. They're both in the same orientation, just dilated. And then the 6 and the 4 go together. All right, let's check our scale factor and see if it's the same for all of them. So for the first one, I'm going to again go ahead and put the top triangle here on top of my ratios. 7.5 over 5. Now, when we go ahead and figure out the scale factor for this one, sometimes when you have decimals, it's easy to just go ahead and divide that out in your calculator and get a number. So let's do that. So I'm going to go ahead and divide 7.5 divided by 5, and I get 1.5. So we got a scale factor of 1.5. So technically it's 1.5 to 1. There's our scale factor, 1.5 to 1. You could just write it as 1.5 as well. If every fraction is 1.5, we're good to go. Let's try the next one. So now we got 4.5 was our smallest side, and that goes together with 3. I'll put that in my calculator. 4.5 divided by 3, and I've got 1.5. So our scale factor is 1.5 to 1. And then let's do the final one. So now I've got 6. There's my unmarked side. 6 divided by 4. Let's check it out. 6 divided by 4 is equal to 1.5 as well. Hey, that worked out pretty well. And you can see if we want to make a mark here, or make a note here, same, and I'll just abbreviate same scale factor. Okay, if it's the same scale factor, then we can say, so they are similar by, and you have to tell me the theorem, by SSS theorem. You're probably wondering, well, how come I wrote on the first one, then they are similar by SSS? Now I said, so they are. There's no set rule on how you write this, class. As long as you declare or write in your sentence, either they are or they aren't. You can say they are not similar, or you can say they are similar by, and just say what the theorem is. But you can't just write that. You got to show the proof behind it, and then make your statement of whether they are similar or not, and then say which theorem did you use to prove similarity. So there's proof of similarity by comparing the three sides of two triangles. All right, let's take a look at the next one. We can also use the SAS similarity theorem. And SAS, that matches our congruence one as well. We had an SAS congruence theorem as well. And it's the same kind of a description, except for now instead of the sides being congruent, they're going to be proportional. If two sides of one triangle are proportional to two sides of another triangle and the included angles are congruent, then the triangles must be similar. So remember, included angle means the angle in between the two sides. So let's go ahead and follow our strategy for this one. Okay, same thing. I'm going to pick the biggest side of both triangles. Now, here's where you can mess up. Take a look at the first triangle. The biggest side I know is 24. Oh, first of all, we better realize that we do have SAS. We have two sides and the included angle, and two sides and the included angle. If we don't have two sides and the included angle, there's no reason to even try SAS because you don't have enough information. So 24, now your brain's going to want to circle 24, but remember, we're circling the biggest side. 24 goes with 32. And then the only other side that's left is 18, and that goes together with this side. The third side is not marked, and we don't need it. We just need two sides. All right, let's check our scale factor. So now I'm going to go ahead and do like I've done before. I'm going to take the big side of the first triangle and divide it by the big side of the second triangle. Now, probably, class, let me just go over something with you. Probably the better strategy is always putting the bigger number on top. So I'm going to flip this around. I'm going to go ahead and say, you know what? I'm going to choose to put 32 on top and 24 on bottom. And let's see what we get. So we got 32 divided by 24 is equal to, now it's 1.3333. I'm glad this came up. Now you see this, you're going to write it as 1.33, but you know this was a repeating 3. So this is, in fact, we can write it this way, 1.3. Let's put a line there so we know it's 1 with a repeating 3. Okay? Now, when we check our other sides, we have to remember we picked 32. That was from the bottom triangle. So now when we compare the other two sides, we have to pick a number from the bottom triangle. We can't flip it around and now start with the top triangle. Otherwise, we're going to be flipping our ratios around. So if we use 32 here on top, we have to pick from the same triangle and say, okay, then I'm going to check 24 over 18. Now it will work either way. I want to let you know. If you did 24 over 13, in fact, you know what? We'll check that in a moment. I'm going to show you guys that it doesn't matter which way you go. Let's do 24 divided by 18. And we got 1 with a repeating 3. That's also 1 with a repeating 3. And so now we can go ahead and say, hey, based on this, we've got same scale factor. Now we're not done because now we have to check the included angle. Let's go ahead and label that. So I'm going to call this one A. Let's give this a different color. Let's call this one A. Let's call this one A prime. Just because we're trying to see if we have similarity here, that's fine. So A and A prime. Actually, you know what? I'm going to change that because the problem is that makes you think that one of them is the pre-image, and we don't know that. Let's name this one angle B. Then we don't have that confusion. Okay, our included angles are A and B, and we see that angle A is definitely congruent to angle B. And that is the included angle. In fact, let's do this. Let me change this a second. Sorry, that's not what I wanted to do. I'm going to leave some space here. Let's put this as the included angle. Included angle. That way we know we're actually checking those two. And they are congruent. So now we've got two sides that are proportional and the included angle is congruent. So we can actually write our final answer. So the triangles are similar by the SAS theorem. Again, there's all kinds of ways you can write that. Just make a statement whether you found it to be true or not. Okay, there's how you use SAS to prove similarity. Let's check that out in the next example. So final example, are these two triangles similar? Okay, let's take a look. Let's go ahead and match up our sides first. So we'll say, okay, here's our biggest side is 16. Here's our biggest side is 24. Let's match up our smallest side. This is the smallest of the sides we know. Oops, I should change that color. This is the smallest side that I know. Why is it not changing color? Let's try again. Oh, I know why. Here we go. Now it's time. Here we go. And that goes with 12. Let's take a look at our included angle. Oh, we got a problem. Our included angle, this angle is included. Angle X is included between the two sides. But the 94 degrees, that needed to go right here. And that's not where it is. We don't know what the included angle F is. So because of that, we don't know whether they're similar or not. Now, it's common that students will write here, therefore, or so, these triangles are not similar. We can't say they're not similar. What we can say is we don't know if they're similar. So we're going to put on here, we cannot prove similar because, and let's label, this is labeled E, because angle E is not, correct that, is not the included angle. So you saw in the previous example, you saw how we can prove they're similar, but in this case, we don't have an included angle down in the bottom triangle. It's not the included angle, so we don't have enough information. If they had given us the angle F and it was 94, we could proceed with our checking for proportional sides. But in this case, we cannot verify that they are similar because angle E is not the included angle. And I can tell you right now, if you compared 16 over 24, and you found that scale factor, and then you compared 8 over 12, you would have gotten 0.66, actually repeating 0.6. So you would have found that the corresponding sides are proportional, but we don't have an included angle. And then last thing, sorry, it was a long video, but let's go back to this one. I just want to show you what happens if you decided to flip these around. So what if you actually did this and said, I'm going to check 24 over 32 for this one, and for this one, I'm going to check 18 over 24. I flipped it, and now I'm looking at the small triangle on top and a little bit bigger triangle on bottom. Now put those in your calculator. You're going to see you're still going to get similarity. Hang on a second here as I drag this over. Sorry, got a little bit problem here. All right, let's do this. We got 24 divided by 32, and that's 0.75. So 0.75, and then I'm going to go ahead and do 18 divided by 24. 18 divided by 24. And you can see, same thing, 0.75. So you still can prove proportionality if you flip both of these over. You're going to get a different number. Think about this. The reason you're getting a different number is because the scale factor is different when you go from the small triangle to the big one compared to going from the big one to the small one. So you can see it doesn't matter which way you go, as long as whatever triangle you put on top of your first ratio, you keep that triangle measurement on top of all the other ratios. So there's some ways of proving triangles are similar by shortcuts and using the same methods to figure out, hey, we don't know whether they're similar if we haven't been given enough information.